ঠিক আছে স্যার।
হ্যাঁ, so let's begin my today's session with the discussion of statistical quality control, and I am going to discuss the portion which is as being shown in front of you on the screen with article 16.5, which talks about X bar and R or S control charts. Today I'm going to discuss about X bar and R control charts, and I'm just in the beginning of this session, I'm just going to scroll down the sections which I'm going to discuss by doing some calculations in the whiteboard. So I'm going to discuss this equation 16.2, and then I'm going to discuss about what is X bar chart, and then I'm going to discuss about this quantity which is denoted by mu cap, written in 16.3 equation number, and then I'm going to discuss about 16.5 and 16.6. These are the equations which I'm going to discuss. And lastly, our final equation, or whatever you can say, it's a kind of formula, which is this written in equation 16.9. So this is our formula of today's class, and I'm going to discuss everything about these things in three successive sessions, because this Zoom I'm using, it's a trial version, and therefore I have, after 40 minutes of limit, it will be disconnected automatically. So I don't know, probably Tushar hasn't participated in my last class, so I'm telling Tushar that after completion of each session, you have to rejoin by clicking on the link. Okay, so therefore it is for your kind information. The other student Bonnie, she already attended the last class, and therefore she already knows that she knows the rule. So I'm going to discuss all this, but if I present the page and I keep on discussing about these things, like I mean, what is UCL, LCL, CL? These things, if the discussion of this by presenting a note would be not feasible, because since it is a mathematics class, so I have to do mathematics. Otherwise, you will not understand. So let me stop the share, and let us go to the whiteboard where I'm going to do some board work. Now, as Tushar joined in today's class, so therefore for him, I'm telling that in my last class, we started this section, the statistical quality control, which is there in short, it is sometimes also known as SQC. Sometimes it is known as SQC, and we discussed about why we study statistical quality control and did a basic problem. So I am telling you that now is there. Now he has left. Okay, I was talking to him and he has left. So, anyways, Bonni, let us continue with our current discussion of statistical quality control. And in statistical quality control, two important things, as you will see in the note. One, in this particular part, we actually try to control two different things. We control two different things, One, as you know, as I told in the last class, that one is called mean value of the quality characteristic, mean value of the quality characteristic, and number two, the process variability. The process variability. Everything which I'm discussing right now, it's on the basis of the note which I shared with you, and the page number which I just presented. The page number on your note is As I can see, it is the page number is not mentioned over here. I'm going to discuss about the equations 16, 1, 2, 3, which is there in the note I shared with you. So those who joined late, they may be puzzled which particular part I'm discussing right now. So for them, this is the information that the note which I shared in last week. There you find the equation 16, 16.2, 16.3. These notes are being discussed mathematically on the whiteboard. So by statistical quality control, we actually try to control two different things. One is called the mean value of the quality characteristic, and another is called the process variability. You try to, if you are copying anything, then you try to copy quickly, because I have to do lots of calculations, so I will fluctuate between the pages. So therefore, you have to speed up your writing. Okay, so let's continue with this. Mean value of the quality characteristic is actually studied by this chart, X bar chart, and the process variability is studied by this chart, which is called R chart. That is the difference. That is the difference between X bar chart and R chart. X bar chart helps you to study the mean value of the quality characteristic, and R chart helps you to study the process variability. In our last class, we actually discussed that if you have a mean, if you know the mean of some items, mean of a sample, then what we do actually, we consider the mean to be mu, and we can find with respect to this value mu, which is called the mean, which this is actually the average or mean. When we talk about average, we consider the mean, ordinary mean, arithmetic mean. Okay, now this sometimes this average can be median also, mode also, but we shall try to stick to the arithmetic mean in this discussion of statistical quality control. So if mu, and this notation which I have written over here is called mu, it is the Greek letter. So if mu is the average or mean, then this is actually termed as the central limit. You already know it. This is called the central limit. And with respect to mu, we can try to define two other values on within which the mu will lie. How do we calculate the values? If sigma is the standard deviation, and which we know that standard deviation is nothing but the square root of variance. All these terms have been discussed in the last class. So corresponding to this central limit, then we calculate these quantities mu minus sigma and mu plus sigma, or we can calculate these quantities mu minus 2 sigma, mu plus 2 sigma, or sometimes we calculate mu minus 3 sigma and mu plus 3 sigma, so that this value mu lies between them. Okay, mu is lying between either mu minus sigma and mu plus sigma. So it is basically equidistant from mu. Mu minus 2 sigma or mu plus 2 sigma equidistant from mu. Mu minus 3 sigma, mu plus 3 sigma equidistant from mu. So we can calculate these things. Okay. Now, also I discussed in the last class that these quantities mu minus sigma, mu minus 2 sigma, mu minus 3 sigma, these quantities are actually called LCL, or lower control limit. Okay. And these quantities are called UCL, upper control limit. These things we discussed in the last class. Okay. And also at some point, I also told you that it would be nice if nothing is mentioned, about which particular limit, which particular formula we should choose to study statistical quality control. Probably you can recall, and if you do not recall it, then let me tell you right now that if nothing is mentioned, it is best to use the following control limits for study of following control limits to study this quality characteristics. Which of these three limits we actually choose? If nothing is mentioned, we actually choose central limit remains fixed always, we call it mu, but for UCL we choose mu plus 3 sigma, and LCL gives you mu minus 3 sigma. So this is often actually used. And also I must tell you that all these things, all these limits actually come from the study of normal distribution, which is actually a probability distribution, and normal curve actually looks like this. So if you think about the normal curve, okay, so this is your mu, this is the central limit, and this quantity is called mu minus 3 sigma, and this quantity, say I'm roughly drawing, it is mu plus 3 sigma. Okay, so this part is equidistant, this part and that part is equidistant from mu. And if you want to calculate the distance, total distance from this point to that point, this total distance is actually how much? It is the distance between the distance between the points mu minus 3 sigma and mu plus 3 sigma is actually mu plus 3 sigma minus mu minus 3 sigma, and that it is equal to mu plus 3 sigma minus mu plus 3 sigma, that is 6 sigma. And therefore such a control chart, when you use this particular results, upper control limit, lower control limit, and central limit, you use this part, then such a control chart is sometimes called such a control chart is sometimes called 6 sigma control chart. 6 sigma control charts in general. So this X bar chart, which I have written over here, is a kind of 6 sigma control chart. R chart is a kind of 6 sigma control chart. All fall in the category of 6 sigma control chart. Okay, X bar chart with the formula, if you look at the formula in the book or in the note which I have shared, it is a kind of 6 sigma control chart. You will get to see. And R chart is also a kind of 6 sigma control chart. Okay, so therefore that is the basis of a statistical quality control, and you have to know this. And it is also very important for MCQ. This particular note which I have written over here, it's also very important for MCQ type of questions. Now we shall try to deal with this particular formula, that is CL equal to mu, UCL equal to mu plus 3 sigma, LCL equals to mu minus 3 sigma. Okay, we'll try to understand how do we calculate this. In the last class, I discussed a few things about that, but today I'm going to discuss in details. Okay. Now, why this? What do we mean by? First of all, you have to understand what do we mean by the mean value of the quality characteristic and the process variability. So when you manufacture something in the factory, and you get the products, these products may be defective, maybe non-defective. Now, when this product can be, you try to think about this experimentation from your subject matter, that is food technology. And let me talk about, I can visualize this subject matter from my perspective. So from your perspective, when you are actually producing a food product from your lab, these food products, various food products are being manufactured. A kind of food products is being manufactured per day in your factory. Then some products quality may be defective, some may be non-defective. if you are actually calculating, if you are actually producing 1,000 items of those, then it is not possible for you to uh, tell immediately by guessing that how many items of these 1,000 items are defective and how many are non-defective. So to maintain the quality, you actually go for the quality control. So you have to study the quality first, and then you have to control it. In the last class, I told you that there are two types of uh, causes which affect this quality. One is called the chance cause, which is inherent, that cannot be controlled, and another cause is called the assignable causes, artificial causes, man-made causes that can be controlled. Okay, if you say that we actually teach students in the college, and the students come out of the college, and we want to check whether these students are can deal with the practical problems or not, this is kind of also, it's also kind of, I mean, uh, this particular experimentation also falls under this category. So for example, why do we take internal tests? Is it because it is in the protocol of of McCout or in any other university? No, we check the quality. We check the quality, and we try to tell students, these are your defects, try to improve yourself. Okay, so therefore it's also a kind of statistical quality control, where we take different examinations with different internal tests are conducted, and we take students and we try to improve them. Now we take examination of all the students. Some students perform well, some students don't. Then we again take the examination. Then also we are seeing that some students consistently are not performing well, some students consistently perform well. We choose the good students and we try to motivate them further. Okay, that is the usual practice, and we try to encourage the non-performing students as well, and try to tell them whether he listens to me or not, that is a different issue, but we try to tell him that, yeah, you are lagging behind, you just improve yourself. So we are also actually maintaining quality. But when it is a matter of a non-living thing which is being manufactured in the factory, and very many such items are being prepared, so it is not possible for me to deal with all the items. So what we do actually, take the sample. We take the sample, we study the sample. On the basis of the sample, we declare about our population. If my sample is telling me that something is there which is not up to the mark, we go back to the manufacturing process and we try to find out the defect, because there are three assignable causes, in the last class I discussed. So we try to find out which assignable causes is actually affecting, and try to improve it. The students who are actually are, for the first time they are attending my class, I can tell briefly that why there are three types of assignable causes. So for example, again from my perspective, if the student is not performing well, then there may be three issues. Maybe the IQ of the student is not good, so I have to guide him properly. Maybe I am not good. Okay, my teaching is not good, not up to the mark. Then I have to enroll myself in the faculty development program and try to improve myself. Or maybe the system is not good. Okay, lack of proper classes, the proper labs, everything that's not being maintained in the college or in any institution. So we have to talk about that. We have to tell management, so maintain this. Students are not able to perform the lab. So these are called the assignable causes. Okay, but what are the chance causes? Let me repeat. Chance causes are kind of from this educational perspective. Suppose student is good, IQ is very fantastic IQ the student has, teacher is fantastic, manage the I mean this system is very fantastic. Okay, just like your food technology department has got NBA accreditation in this year. So we have, after Jadavpur University, we have fantastic laboratories in our college. But COVID-19, this lockdown, this is the chance cause. We cannot control it. So chance cause cannot be controlled, but assignable causes can be controlled. We have to find out which assignable causes is actually affecting the quality of the product which come out of the factory, and we have to deal with that. So I have intentionally given this brief reintroduction of the topic so that you all can copy whatever is written on the board. So now I'm going to switch over to the next page and let's continue with mathematics, because I'm a mathematics teacher and therefore I can only talk about that. Okay, I cannot talk lines after lines on a particular topic for several hours. I can do lines after lines maths for several hours. Okay. So so first case is one, there is a case. I have to deal with two cases. There is a case. So first of all, the case is that population, you will see in the note that it is written. If you read all the lines, you'll get to see it, otherwise not. So population mean mu and population standard deviation sigma, population standard deviation sigma, these two items are known, are known, and it is assumed, it is assumed that we are dealing with normal population, normal population. Now, students, I must tell you that since the statistical quality control is actually a topic which is the last topic of the, I mean, I'm using a book by C. Montgomery. I don't know whether you'll be able to see this or not properly. This book I'm using, and from this book, I'm actually giving you the notes. So statistical quality control is actually the last topic of this particular book. So it means that the basis of these notes, the basis of these chapters lies in many previous chapters. Okay, so you have to understand the previous topics. You have to understand about, you have to know many terms about statistics. Some terms I'm using over here. It's because if you are understanding, if you have dealt with statistics, probably you know this term. But if you have not dealt with statistics, you are not acquainted with these terms. But you don't have to worry, because the other teacher is going to teach you a module 1 and module 2, and there she will be discussing about these terms like normal. Say for example, I'm concerned about this term normal population. So she is going to discuss about that. But since I'm using this term normal population, so let me talk a few things about this. Now, normal population, don't think that don't think like this, that it is a population which contains normal people, and the population containing abnormal people is abnormal population. There is no such thing like abnormal population. Normal population means, this term normal population mean the population is following normal distribution. Normal distribution is a kind of probability distribution. Normal distribution whose graph looks like this. Normal curve looks like this, and probably probably in TV channels you have got to see this kind of graphs. Okay, so I'm talking with respect to this COVID-19 situation. So often we get to see these graphs in newspapers, TV channels. So if population is following normal distribution, then that population is called normal population. Normal distribution is a type of continuous probability distribution. Continuous probability distribution. So madam is going to talk about it in details. Okay, so this is not in my jurisdiction, so I'm not going to talk about it. So this is a kind of you can tick on it, and you can say that this is a kind of prerequisite which you get to know for better understanding of statistical quality control. But that will not hamper or you in dealing with the maths of SQC, because I will tell you the technicalities. You can do the maths easily, but for understanding, you have to deal with this also. And what is population? Population means that a kind group which contains all the items, as you can imagine. Okay, this population can be infinite, this population can be finite. Now, when we talk about the items produced in a factory, then I'm actually talking about, I may talk about the finite population or infinite population. Okay, so if you ask me that what is finite population, it is very easy to understand what is finite population. A group containing finite number of items. Say for example, I am considering the data. I am considering the data starting from the year 2010 till 2020. This 10 years data has been chosen, and suppose my factory is actually manufacturing an item, a particular item. This can be any item. It can be a screw, it can be a refrigerator, anything. And we know the quality. We have dealt with these many items from for last 10 years, and we know that some parts of that refrigerator or some part of that screw, okay, has average value, has some kind of average value, and some kind of variability in it. We have got to see it from the past experiences, from past data. Now we can call this particular data from the year 2010 and 2020 can be is a population, and that population is a finite population, obviously. Okay, and suppose that average value is mu and that value is sigma. So from our past experience, we can say that this mu is known to me and that sigma is also known to me. Okay. Also, if I talk about infinite population, so that infinite population do not have any limit of data. It can be, we can consider any data hypothetical. This infinite population is actually a hypothetical, and often it is actually, this hypothetical means it is often, whatever we say, we actually assume it. We assume it. Okay. So for example, let us talk about here also average is there and variability is there. So let me tell you about why do we mean by infinite population. Say for example, if I ask you that what is the percentage of men who smoke actually, so you don't have to have any, we don't have to have any kind of experience for that. I mean, don't have to know any particular details. From your experience, you will immediately say almost, you will say almost every male smoke. Or some people may say that okay, 95% of male they smoke. Obviously they have to be, I am considering all the adults, not the minors or juveniles. So we can say that almost. So how can I say it? From our experience, we have seen here and there on the road. Okay, we have seen at our home also. So from our experience in the TV channels, we actually know it, some kind of thing. So that is, so what is the what is the percentage? You are saying the 95% of the population. So where this is, which population you are talking about? Population of all male. Okay, so this value of the population, how many male you are considering, that you don't know. You don't know about that. You only know about the percentage. If I consider 100 males, then 95 smoke. Okay, in terms of percentage. But actually what population you are dealing with, you do not know. So that population is called a hypothetical infinite population, because size is not known to me. So here also, if I can talk about mu, and here also if I can talk about sigma, and that mu is actually known, and sigma is also known. And if I deal with such a population, if I deal with such a finite or infinite population, then if I deal with such a finite or infinite population, then we say that in this case, the central limit, you will see in the book that central limit is given by mu plus 3 sigma by root n. Okay, for X bar chart, I'm writing this particular formula. Okay, for X bar chart, because if you see the previous page, I only wrote mu plus 3 sigma. That is the general structure. But if I talk about X bar chart, I am going to put it in this manner. So this is your UCL. Your CL will be mu, and your LCL, this will be mu minus 3 sigma by root n. Okay. This formula of finding the limits, upper control limit and lower control limit, only can be applied if mu is known and sigma is known. Sigma is known. But if they are unknown, what we have to do? Because most of the time, these values mu and sigma will be unknown to us. This calculation, okay, there is another prerequisite. This particular thing which I've written, it also requires a kind of prerequisite. So what is the prerequisite? Let me talk about it. The prerequisite is called the central limit theorem. It is called the central limit theorem. This formula is coming from central limit theorem. Okay. Again, it will be taught to you by the other teacher. Central limit theorem says that the statement of the central limit theorem is that the standard deviation of the population will be having this kind of structure form. So the standard, if sigma is the standard deviation, it will be divided by, I mean, very roughly I'm speaking, because if I talk about central limit theorem, then I have to talk about many things. So this particular part will change. Sigma, we shall not write sigma only. We'll divide the quantity sigma, the standard deviation, by the square root of the sample size, the positive square root of the sample size. Okay, so that part you have to know. I'm putting a star mark over here. In the last class, we dealt with problems. You calculated, if you can recall, you calculated mu minus sigma and mu plus sigma. That was in general. Now, if I ask you to write the upper control limit and lower control limit of the X bar chart, then you have to multiply that sigma by the quantity. You have to multiply the sigma by the quantity 3 by root n. That is the difference. That is the difference. Root n, or Bonni Chatterjee is written, what is root n? So suppose, okay, fine. If n is here actually the sample size, okay. So suppose your sample size is, 4, then your root n will be positive square root of 4, that is 2. Because n is the sample size, and therefore it has to be positive, because you cannot say that I have gone to market and I have bought minus 10 bags. Okay, so if that has to be positive, so its square root also has to be positive. So it is a positive of, it is square root of the sample size, actually square root of the sample size. So we multiply by this quantity 3 sigma. If you talk about 3 sigma, then actually we will say that we are actually dividing this item 3 sigma by this quantity root n. And this, why this is so, why do we divide the quantity by root n? The logic comes from the central limit theorem. That's why I'm asking you to go through this particular statement. You can search it in Google also, or you can take out any statistics book, and you can see it in the index. The central limit theorem has to be there in every statistics book, and you have to read it. Or the other teacher is going to discuss about central limit theorem in her class. Okay, so it is there in your syllabus in module 1 and module 2, so you don't have to worry much. I am not going to discuss about the calculation regarding that. Okay, so I'm not going to discuss about this particular case in details because calculations have been discussed earlier. But although since there are few students who have joined in my today's class, say Tushar is there, Nadira couldn't join properly in the last class. So for them, I'm actually saying that quickly. I'm saying that uh, uh, I'm asking all of you to quickly calculate this thing. Calculate upper control limit and LCL, the lower control limit, uh, when mu is I mean 1.5 and sigma is 0.5. Okay, and sample size is, say for example, 2. I am selecting very small values because it is always good to think about maths with small values. We can deal with large values later once you are comfortable with small values. And I'm since you see that mu and sigma are known, and we are going to find UCL and LCL. So immediately we know that CL is actually nothing but the sigma itself. So CL is known. So one part is already done. The second part will be UCL. UCL will be mu minus mu plus 3 sigma by root n, and so therefore this can be calculated as 1.5 plus 3 into zero point 0.5, okay, by root over 2. You can calculate this term very easily, and LCL will be mu minus 3 sigma by root n, which is 1.5 minus 3 into zero point 0.5 by root 2. You can calculate this term very easily. Okay, so if I calculate these terms, so let me see what is coming. 1.5 minus, you can also do it along with me, 3 into zero point 0.5 by root 2. So this quantity will be 0.4393, and the other one will be 1.5 plus, inside bracket you write 3 into zero point 0.5 by root 2. So that will be 2.56 2.56 2.5606. Okay, and after that what we do, you already know, we draw a kind of, we draw axis, and or you do, you draw on the graph, you draw this line. We call this line as, mu, and we somewhere we put this value mu minus 3 sigma, and we put this value mu plus 3 sigma, above and mu minus 3 sigma below. So you are going to put it mu plus 3 sigma by root n and mu minus 3 sigma by root n in the graph like this. Oh, minus is coming. Okay, so okay, minus, yeah, all right, that will be plus and this would be minus. So we shall continue our discussion because this session is going to end soon. We are going to continue in the next session. Okay.